So welcome to Applied TensorFlow in Android apps. Today we're going to do a very quick intro to machine learning, and then we're going to concentrate on building things. Today's talk, we've only got 40 minutes, it's really short, so the machine learning intro is really basic. So if you want more, I did a talk a couple of months ago. It had a 30-minute introduction to machine learning, so if you have unanswered questions or you just want to find out more, you can go check that out. There's a screencast of it on YouTube. But for today, we're just going to talk about supervised, unsupervised, and reinforcement learning for our intro. You need to know about these because any conversation about machine learning, people are going to ask you which one you're doing, and you need to know. So supervised learning, in this example, our training data is already labeled in some way. So a typical example would be you have a bunch of x, y values, and then you're going to be training your model, and it's going to effectively fit a line to those points. And then you're going to have a new value and say, hey, what's the prediction for this value? And based on that model, which is the line, it will give you your prediction. Another classic supervised learning situation is classification. So you have lots of images of dogs and lots of images of not dogs. And you feed all those into your machine learning model, and it's going to learn to differentiate them. And then you can pass it images it hasn't seen before and ask it, how confident are you this is a dog or not a dog? So the difference here between regression and classification, regression is predicting a value and classification is predicting a label. So let's look at an example of supervised learning. So the TensorFlow project has a really good Android demo app. I'm going to show you a little video of it now. The thing at the top, the blue bar, this has the predictions of what object it thinks it's seeing with the camera. And then on the right, we've got the confidence for that prediction. So here, this would be a 40% confidence. It's a coffee mug. So let's have a look. There's no audio for this one. We can see here it's doing a good job seeing coffee mug cup, espresso. Running shoe, 99% confident this is a running shoe. This model was trained on 1,000 different image categories. So it hasn't seen a USB cable before. That's why it just has no idea what it's looking at. This is tomato, but it thinks it's a bell pepper. And I think it's probably because there was no tomato in the training set for this particular one. What I'm doing in the video is I'm trying to break the green stem off because I was thinking, oh, maybe the green stem is throwing it off. It thinks it's a bell pepper. No, it really thinks it's a bell pepper. So I think that's just a training data issue. Key thing about this app, you can go download it from Nightly Builds. Anyone can go grab it on their phone. It's about 90 megabytes, the model inside of this, so it's pretty big. But it works 100% offline. You do not need to be online to use it, which is just amazing. So unsupervised learning. In this situation, we haven't tried to label our input data. You just dispatch the model to go look at it and figure something out. So the main example is clustering. So we'll give it all of these different kinds of images and say, go group them together based on which ones have the most similarities. So in this example, we're doing animals, but in the same way that we cluster images, we can cluster things like viewing habits of video and music streaming services. So this is something they might do behind the scenes to predict which kinds of films you might like based on others you've watched, because they've clustered them all together. There's also some quite counterintuitive things that you can figure out from this. So you can actually train a face detector without labeling data as faces. So a bunch of Google folks and academics back in 2012 took hundreds of thousands of video frames from YouTube, and they sent an unsupervised learning algorithm on it, and it grouped all the faces together. Like, it didn't tell it to do it, it just grouped all the faces together. So it's kind of mind-blowing. And I've highlighted Andrew Ng because he's got a famous online machine learning course, so he's quite famous in the field. I don't have a video for that one. So for reinforcement learning, this is the third type. Anything with a reward function you can train. So I'm going to show you a video now. What we've got is this blue pole is hanging underneath the cart. Here is a 0 reward. As it swings up, it gets more reward. And when it's at the top, it gets its maximum reward. So let's take a look at this one. I've shortened the video just to make it fit in this presentation a bit easier. So initially what it's doing is it's just doing some random moves left and right, and it's just seeing, oh look, I got some reward, the pole swung a bit. And over time, it gets a little bit better, and it's reinforcing the behaviors that give it a higher reward. I love this video. So for this one, it took about 1 hour of real-world training to get to the final controller, which we're going to see in a minute. And it took about 10 hours of CPU time, I think, to number crunch for it. So here, it's 180th of 10, and you can see it's already doing a really good job. That's one of the best videos I've seen. I love it. So anything with a reward function or a score, you can train in this way. So classic example is all the like Atari games, computer games. And I just want to make it clear, you don't have to tell it what's happening in the game. You feed the model the frames from the video and the score, and it will go figure it out. It's amazing. So recap: supervised learning, labeled data; unsupervised learning, data only; and reinforcement learning, you've got a reward function. So how does this fit in the bigger picture? In the bigger picture, you are typically going to get your training data, which, as Zach was saying in the earlier talk, that's actually often a really hard thing to do. You've got to prepare it in some way, you've got to do the training, and then you typically reserve some percentage of your training data to do the testing with. And that testing is just checking, like, did my model generalize? Is it going to do a good job when I give it some other unseen data? And then you iterate to improve. And at most companies, what's going to happen is some other team are going to do this for you. You've probably got like a machine learning or a data science team, and they're going to get this model ready and do all the optimization, and then they get to the end and they want to release it to production, maybe to an API or give it to you to put in your Android app. But that's typically the flow. You don't have to do it that way, but that's the typical process. There are lots of machine learning frameworks. We're in the Google ecosystem, so we're going to be talking about TensorFlow today. It's really good for tutorials, great support from the community. It works cross-platform everywhere, including Android things, which is super cool. It's built to scale, so you could be working on your laptop and then just deploy this thing to the cloud in some like TPU giant machine that will run everything in parallel. It's seamless to go from small scale to big scale. The actual training is done in Python or C++. Google like to use Bazel as their build tool, which can feel a little bit unfamiliar if you haven't used it before. You generally only need to do that for training, though. You don't need to build the Android demo project with that anymore. And when you're using it on Android, you need to use the NDK. That sounds scary, but again, this has got a lot easier in the last few months. So you're actually going to find out later that's easy. So gotchas, if you're using a tutorial that's over about 6 months old, watch out, because there's been changes as they finish the final release version of TensorFlow 1.0. So make sure you're using an official tutorial or something new. Zach's talk earlier, he was doing something that wasn't an image classifier, and he had a really small model, which was awesome. But for the image classifiers, by default, they're still quite big. And there are ways to shrink them, but I haven't actually gone through all the steps yet to figure out how small they'll get, but I think you'll be able to get them a lot smaller than that. So we talked a bit about the machine learning basics. Like, what are the ways we can use machine learning in our app? This isn't to do with TensorFlow, but you could use a cloud-based API. Like, that's the obvious starting point. There's something you want to do, someone shrink wrapped it for you. Machine learning as a service. We're going to talk about that. The next easiest, I'm doing these in order of difficulty. The next easiest is take a pre-trained model that someone else has built and drop it into your app. Next one is, going a bit further, you could do some of the training yourself, and you probably want to start by just following a set of instructions, because it can be really hard to start from scratch. Next version, you kind of customize something you've already seen. And then there's two more you can do, which we're not going to discuss today, but for completeness, you could train completely from scratch, like the way Zach did in the previous talk. Or you could train your model on the device. Like, there are ways to do that too. So 1 to 4 we're going to do today. So the first one, use the cloud. The 4 big providers all have these APIs that are kind of built for an enterprise team. You would they're very powerful, but they're not tied to one specific use case, and they're not really going to be a good fit for just sort of a small group of developers. The good news is the Google and the IBM APIs, they have some much more focused shrink wrap ones. We're at droidCon, so we're going to talk about the Google ones. 7 of them up there. I'm just going to give you a quick intro to a couple of them. The best thing I like about them actually is that Google have built web pages so that you could just try them out without integrating, which is really super useful. So for the Vision API, you could just go in, drop an image in, and it's going to auto tag it with all the things that it's found in the same way that we looked at that demo app earlier. It's doing object recognition. It's going to give you sentiment analysis and detect all the faces. You can see all the tabs along the top for the different things it has. And if you've used Google Photos, it's using the same technology behind the scenes. So what it's doing is it's auto-indexing all your photos and figuring out what's in them. And I didn't label these in any way. I just type monster truck, type beach, boom, it just finds it. Red selfie, pizza, you name it. It's a really awesome feature. Natural language API, so you can just drop some text in. It's going to extract all of the entities that it sees based on Google's knowledge graph or Wikipedia. It's going to show you the sentiment. This one is strongly positive, the green 0.9. And then a syntax tree. So all kinds of cool stuff, but we want to do more than that. Like, we want to go a little bit further. So using a pre-trained model, let's look at a project to help us understand how all these things fit together. In this one, what we're doing is we have a digit handwriting classifier. So drawing digits, pressing detect, and it generally does a really good job. When we get to 5, I've made it a bit difficult. I'm going to draw some bad numbers, and it's going to struggle and put down an 8. But overall, it does okay. It's not meant to be perfect. But what we're going to do is we're going to dip into this project in more detail and see how the pieces stick together. And there it got it. So here's the repo for it. You see MNIST in the title up here, and MNIST in the title here. What is that about? So NIST is the National Institute of Standards and Technology. Back in 1995, they got 800,000 character writing samples from Census Bureau employees and from high school students. And they distributed it on a CD-ROM. It's fun to think of. And then somebody created a subset, which is a bit more normalized. And I'm telling you about this because anytime you read about machine learning training, you're going to hear people mention this. It's a very standard training set. So back to the project. What's the architecture? What's going on here? So we've got the Android part on the left, where we've got all our app code. And then, as I mentioned earlier, you need the NDK. So deep down inside native code, we've got our TensorFlow graph. So to talk between SDK and NDK, we need our Java native interface. This is all scary. You don't need to know about it, but this is what's happening. We're passing in some pixel data of what the user's drawn. It's going through the JNI wrapper. It's going into TensorFlow, and then TensorFlow's returning out its classifications and its confidence. And just a little side note, graph and model, you can use them pretty much interchangeably. Machine learning model, TensorFlow graph, they're all the same thing. So let's look at the project. In our source main assets folder, we can see we have our MNIST model graph.pb. That's the actual model file. .pb means it's a protocol buffer file, which is binary, which is why I'm not showing it on the screen. And then there's the labels file next to it. So this is our 0 to 9 digits, which are the possible classifications that can come out of this particular model. So how do you interact with one of these models? Well, as of, a few months ago, this became super easy. You add a dependency to your project, and then you use this one Java class to interface with the model. So let's look at that in more detail. Obviously, we don't want to use the plus sign on our Gradle dependencies, so you should use 1.2 or maybe 1.3 is the newest one. Both of them would be fine. And then you can see in my build Gradle, I've got the dependency. And the cool thing is you can go in and under your app build folder, intermediates exploded, you can go look what came down in the dependency. So we've got our org TensorFlow, and we've got a JNI folder, and we can see in here that we've got our native code files. The lib.so is a native code file, and the folder that they're in shows you the architectures that are provided. So this is all bundled up inside the dependency. Also, there's a classes jar which has all the classes that come down. I've clicked through to expand the TensorFlow inference interface, and Android Studio here has decompiled it. You could go get it from source code in GitHub as well. There's no reason you need to do this, but it's just quick to get to this way. So what is in this interface? Let's look at the structure view and do the public methods. So first thing we want to do is we want to initialize it. Then we want to feed data in. And the way that they've made this a general interface is they have a different method with each of the types that you can pass in. We then run the inference, and then you can pull out the result. Again, each method is for the different types that could get returned. And then when we're done, we can close it. So let's look at this in a little bit more detail. Where does this code live? So in the project that I just showed you guys, there's a TensorFlow image classifier class, and that's where all this code lives. This is almost identical, if not identical, to the Android TensorFlow demo app, so it's all the same code. So the first thing we do is we're creating the inference interface. We're passing in the asset manager and the location of the model file. You don't need to know what happens now, but this is what happens if you step in. If you step in, you'll see that it's loading the native code, and these are the files we saw earlier, and the lib on the front and the .sl on the end. It's just how it works. Don't worry about it. And then we open the asset manager, load the file, and create it into a TensorFlow graph. So that's just what's going on, in case anyone cared. Don't try and read this code too quickly. We're going to step through it. So this is where the real meat happens. We've drawn something on screen, and we want to go figure out how it's going to be classified. So recognized image is the method. We need to pass in the pixels of what the person drew, and you can see these big blocks are the pixels. And then ultimately we're going to get out the labels from the classifier. In this case, number 3 is the label. First thing we do is we need to feed in those pixels. Then we're going to run the inference on the interface. And then we copy out the data again. And then I don't think this is actually necessary here, but you then find the best classification. So you'll have seen all these values here, like how do you configure these things? This is not the name of the file. This is the name of the nodes in the graph itself. So if you're in Zach's talk, he showed a bunch of this as well. But typically, the person who gave you the model is going to give you all these values. And the sample project has all the values. But what we're going to do now is just have a little sidebar and talk about TensorBoard, because when someone gives you a model, it's like, hey, I want to know what's going on here. Can I find out? So TensorBoard is this very useful tool that TensorFlow provides. It does lots of things, including what Zach showed earlier, like it will help you monitor the progress of your training, but you can also use it to import the model. And then once you've imported the model, you can browse the graph that's inside of it. So how do you run it? You just run TensorBoard and give it a folder to put stuff in, and then you open your localhost 6006. To use TensorBoard, you have to install it. So if you have something like pip, you can just pip install it as a standalone, or you can use Docker. The only thing to remember with Docker is if you're doing that, you need to tell your container to pass all of its 6006 port traffic out to the local machine, so you'll actually see it show up in your browser. At the moment, I don't think you can use the UI to import the model file. You have to run this script. So you grab this script from GitHub, and you tell it the location of the model you want to view. And you run it, and it says model imported, and then it tells you what command to run. All you're doing is making sure you're using the same log directory that you passed to the script when you start TensorBoard. So there's no rocket science there. So we open our model, and you can see at the top right, it says subgraph 18 nodes. This is kind of giving us a hint that there's something to look at here. And if we double click on the only node we see, it's going to expand and show us what's inside. So we scroll to the bottom, and we can see, oh look, the name of our input node is input. And at the top right, you can see the float here. So this is the type of the input that it has. And you can click around and see all kinds of interesting things here, like 28 by 28 by 1. You can click on nodes and see the same dimension mentioned again. And you can scroll all the way to the top and see, oh, this is our output node. And it's called output, and it has type float. So these things, it's quite nice to be able to visualize what's going on. Which brings us back here. So as I said, you're generally not going to need to figure this out yourself unless you were the person that did the training. Most of the time you'll be given these values. But let's look at what they are for our case. So input name, the input node was called input. Output name, well, we looked earlier, it was called output. Now we need to configure the outputs. So the good news here is we don't need to do this ourselves. You don't need to understand this code, but this is what the project does. It just inspects the TensorFlow graph, gets the output node and the shape, and just gets this all itself. So magic behind the scenes, you don't need to worry about it. Which leaves us just needing to define the input size. So we're in a sample project, so the answer is 28 by 28. We know that. If you were trying to figure this out yourself, you could use TensorBoard or ask somebody or inspect it in different ways. So what is the 28 by 28 here? Well, it's the grid of the pixels that we're passing in. So it's also the exact size of the training data that was used for the model. So if you were trying to guess, you might be able to guess anyway. You'll also see that it was mentioned in various places in TensorBoard too. So lots of things kind of convince us like, oh yeah, this adds up. Like I can see how this works. So this little project is 32 meg. This is distributing all all 4 architectures in it, I think. And you can see the sizes of the different components. I'm pretty sure we can get this model to be a lot smaller, but I haven't gone through all the shrinking steps for it. But I think we can make it quite a bit smaller. Builds quickly. The classifications are quick too. But remember, this is 28 by 28 pixels. If you were doing this with a lot bit more data, I'd imagine this would be a lot slower. So how can we go even further? So we've done that. We're like, oh, I'm getting interested now. I want to figure out how to train one of these models myself. So let's do a really simple example. We're going to install TensorFlow, and then we're going to find a script to run. So everybody recommends you use Docker when you're using TensorFlow. You don't want to corrupt all your dependencies on your development environment, and it's easy to jump between different versions and stuff. So it's a really good idea to use Docker. And when you run Docker, it's kind of like doing a git clone, and you're telling it, like, go get this container from the interwebs. And then Google have this registry of all the containers that they provide. So Docker will pull these down automatically for you. So when we run it, you'll see that we change from being a normal user to a super user, and now we're down inside this Docker container. And if you're kind of looking at that thinking, oh, what's going on there? Well, you can open another terminal or command prompt, do Docker PS, and it'll be like, oh yeah, okay, right, I've got this container running, and that's what this command prompt is showing. So we don't want to close this prompt. We want to keep this open the whole time we're doing our work, because by default, Docker's going to just throw away your changes. I wasted a good few hours on this, so I'd highly recommend if you're going to do this, go read a little bit about Docker before you do it. So now we need to find a training script to run. Good news, the project we were looking at has a training script. It's at the top level in the project, mnist.py. So what happens when we're in our container, we're going to pull it from GitHub, that training script. Now we can just run it. And when we run it, the first thing it's doing is it's downloading its training data. And this is the mnist stuff I showed you all earlier. It pulls all the ones it needs, and then it starts to train. And roughly every 1,000 iterations, it's going to print out how well its training is doing, and it's reserving some of its training set to test its accuracy. So from 1,000 to 10,000, we can see it's gone from like 20% accuracy to mid-80s. Over the next 100,000, it's getting up to the mid-90s, and up to 200,000, it's now in the high 90s accuracy. So that's all cool. Let's have a little look at the script itself. The mnist examples are so widespread, you can just use them as a standard import. And then we're loading those into our mnist variable. And similar configuration that we saw in the Java code. So our input size is 28 by 28, which makes 784. And our output labels, there's 10 of them, which is the 0 to 9 digits. Practically all these scripts have a big while block in the middle of them, which is where the training happens. It's pretty complicated. We're not going to try and go through this. I would definitely struggle. Typically, the whole size of this training script is 150 lines of code, so it's not much, but it's pretty dense. And then the final part of the script is where it's configuring the TensorFlow graph that it's going to create. So it's saying here, this is the input node. It's going to be called input. It has this size, and it's a float. This is the output node, and there's some various TensorFlowy things going on, like a softmax. and then this is the name of the file we're outputting. So it's easy enough to kind of dip in and just see the ins and outs, but the actual mechanics are very, very tricky to follow. So we did enough to do some training. What if we want to do something a bit more sophisticated and try and customize what we're doing? So let's try and pick a real world problem. So since the dawn of time, humans have wanted to know if they're looking at a picture of legs or hot dogs. So we want to train something to help us with this tricky problem. And we have our image classifier from earlier. So this feels like we're in the right direction, okay? So let's go look in here and figure out how it works and see if that gives us any ideas. So TensorFlow have 4 different Android demo apps. TF Classify is the one I showed you earlier. And it says here, it uses the Google Inception model. That's great, cool. So we've got the TensorFlow models folder, and we can see Inceptions in there. So there's all these models available to us when we're using TensorFlow. Let's go find out more about TensorFlow. Inception. So we can look it up, and we have this graphical representation of the graph that is Inception. This is actually a convolutional neural net, if you want its technical name. It was trained on 1,000 image categories from an image classification competition. And if you look at the layers, what's typically being done in these is it starts out defining small features like edges. It's putting them together to make bigger shapes, and then high-level features. And as you go up, it's got more and more high-level description. And then finally, it's going to combine all those high-level features to give you the classifications. So to visualize this, here's a different example, which is for face detection. It's going to start out with the edges. This is very similar to the matrix stuff that was in the camera talk yesterday. And then the edges get turned into a nose, an eye, an ear, and then ultimately the face gets put together. So if we read about this a bit, we'll see that there are ways to retrain the Inception graph, which is very useful to know. So what we can do is we can take that classifier layer at the end and throw it away and just retrain. And if you think about it, this Inception thing was trained on 1,000 categories of, thousands of images for each. So it's trained on millions of images. And all of the complexity of this graph around edges, features, textures is it's all pre-trained in there. And what we're going to do is we're going to reuse that sort of snapshot and put some new data over the top and have some new classifications. This is done following a really good code lab called TensorFlow for Poets. So you can go back and look at that if you like. So what do we need to get from our image classifier that we started with to our legs or hot dogs classifier? We need images, we need training data. So thanks to Stephen Tan for helping collect these for me. We've got 120 images. And this is an example of supervised learning again. So what we've got up here is the folder name. That's where that's the label. You're implying the label by putting it in a folder. I put these in GitHub so people can either add to it or just grab them quickly if they want to follow the steps themselves. We're in a TF files folder here that we're going to pass to our training. So how do we do it? We're going to use Docker again, and there's a couple of differences to the commands I showed you earlier. So first thing is that we're going to pass in a mount to say mount the TF files folder from the Docker container to my local machine. And that's just making it easy for us to pass stuff in and out of the container. Nothing exciting there. And then I'm using my own Docker container, not the standard Google one. I made a few changes. I've added Git and some stuff to make via arrows keys work. And is also built so that 6 months ago or so, if you were building the demo app, you needed to use Bazel and set up the NDK and all these things. So I set it all up in there so you could just pull that and build. It's actually easier than that today. You can use Android Studio to build, but there are just some little niceties in here. It's all documented how I created it, if anyone wants to create their own or just find out. So we're in Docker, we change to the TensorFlow folder, and then we have this big command to do the retraining. And the only bit we care about really is telling it the location of our files to train with. Everything else is copy and pasted. And it's going to run. I think this one took about 20 minutes on my MacBook. And then now we've finished, there's some extra stuff in here. So we've got an Inception folder, which is where we downloaded the Inception model from, the one that we're going to retrain against. Bottlenecks is some caching stuff that happens for the images. And then finally, we've got our newly retrained graph, which is about the size we expect. It's big. And then we've got our labels. And key point here is we lost all our earlier labels. So we now just have legs or hot dogs. So incidentally, this is why Jinyang in Silicon Valley just has a hot dog or not hot dog classifier, because it's easier to do two than to do everything, obviously. So there's a really interesting step. Zach's talk, he talked about freezing the model that you've trained. I've heard it phrased slightly differently when you're using TensorFlow. You can use this strip unused tool to do the same stuff. So if you think about, we were training this with JPEGs. This has a JPEG decoder at the beginning. And we're going to pass it pixels, so we don't need the JPEG layer anymore. There's also a difference between the TensorFlow environment, between desktop and mobile. They don't support all the same operations. So strip unused is basically doing both of those things for us. Before we can use the strip unused tool, we need to build it. So this is a very common pattern in Bazel. We've got Bazel, and we're saying, please build this tool called strip unused. And this magic stuff here is saying, basically making it not run out of memory when you're doing it from within Docker. So that was one of the gotchas. So now that we've built the strip unused tool, we can use the strip unused tool, which is in the Bazel bin folder. And then all we need to do is tell it the location of the graph to run on. So not super complex, although there's a lot going on there. So how do we test this thing? Well, let's assume we use the stripped version and we put it in our app, and we have to go to the beach and we have to take our pants off and lay down and put our legs in shot and hold up the camera. It takes a long time, so you want to be able to do it from the command line. So there's a really useful script in the GitHub repo called label image, and that just allows us to sort of feed images directly to the model to see how they do. So we run the curl command in our Docker container to pull it down, and then we can just pass in the image that we want to look at. So we've got our first image here. These are hot dogs, and the model does really well, 89% confident that they're hot dogs. And so I'm going to give it a pass. The next one, it is wrong. It thinks they're legs, 59% confidence, and yep, fail, unlucky. And this one, you have to look really close, but these are actually legs, not hot dogs. And you can see that it does well here, 91% confidence that they're legs. Here I'm giving it a fail. It's correct, but if you look at the confidence is 50%, and the confidence for the second category is 49%. Like, it doesn't know. It's not confident enough to make me think that's a good result. So overall, I feel like this is almost by luck that it does this well. Like, I'm so skeptical that 120 training images have made it do this well. So I suspect I would need to add a lot more images to make this work. So let's recap. Like, what I actually want you to go away with today, I think machine learning is here. The tooling's getting really good. You can use cloud APIs now. If you can find someone to give you a pre-trained model, you can definitely do that now as well. So there's all kinds of things you can build. You can think about apps where you take your server model and put it in the client, or if you want to train on the device, like, that's a little bit beyond us today, but you should start to think about that now. Like, maybe you should be customizing the UI based on how the person's using the app. You could build something that helps you learn the best time to leave work to get to Metro, because it's learning how long did you spend at the platform before the train arrived and things like that. So I think you should certainly walk away trying to deeply understand 1 and 2, because they're available to you today. 3 and 4 is getting a little bit specialized, so you need to be quite enthusiastic to do that. So everything I've covered here is a blog post, normally in more detail. The slides are already on SpeakerDeck. There's the GitHub repo and the Docker container. I haven't got it up here, but there's also a really good ebook that's free from the person who wrote the TensorFlow for Poets tutorial. I'll change that in a minute and show you where it is. I think it's called Building Mobile Apps for, let me see. Building Mobile Apps with TensorFlow. I can probably drag that on screen. One sec. So this is the ebook, and it gets pretty technical. It assumes quite a lot of familiarity, but it's really good. So I do recommend that too. So yeah, that's the end. I'm happy to take some questions. I actually ended surprisingly 4 minutes early. Lunch is after this, so but in a few minutes people can start to leave for lunch or whatever. But yeah, go for your questions, please. What everyone's hungry, I guess.
On the model size, it was always like 90 megabytes. Can you talk a little bit about what kind of variation you've seen, and does it vary based on classifiers? Like, what drives it?
So the first sample project I showed you was just doing the digit classifying, and that was 13 megabytes. The bigger one, the Inception one, is 90 meg. There's a lot of stuff you can do to make them smaller. So there's kind of two things you can do. One of them is called quantization. So when you're training, I actually have loads of bonus slides, so we're a little bit ahead. So why don't I drop to my appendix? Let me pull this on screen. So when you're training a neural net, what you're doing is you basically have this graph with all these weights on it, right? So let's imagine we were training this neural net for classifying a frog. These slides are from our Center for Machine Learning at Capital One, like an internal team. So to train, we have our features on the left: green, bulging eyes, sharp teeth. We got our frog coming in, and so the frog is very green, it has bulging eyes, but it doesn't have sharp teeth. And so we feed that through, and you basically feed through your data. This is not a frog, and it's a bit green, but it has very sharp teeth. And so you can see that as you're doing this training, you've got all these weights on all the nodes, and those weights are typically like very highly accurate things. And so when you're training, you really care about having all that accuracy because you're doing, I don't know, a million iterations or whatever. But once you finish training it, you can actually snapshot a lot of those. And so quantization basically says you can sort of freeze them in a different way and make all the data sizes smaller, and there's different ways to do it. So that's one way. Most of these things is just loads of nodes with loads of weights, so that will make it smaller. And then the next thing you can do is, in the way that the desktop platform is a bit different to the mobile, there's these ops that Zach talked about them earlier, the ops in the graph. You don't need all the ops when you're doing mobile because you just finished training it. You now know the set of ops that you need to support, so you can strip out a bunch of stuff that's for the ops support. So my understanding is you should be able to make it a lot smaller. So I've seen 10 to 90 meg for the image classifiers. Classifiers that use things like text or whatever, I would imagine to be a lot smaller, but mileage may vary. That would be. I'm planning to do a blog post on this at some later point. I need to go and try out all the stuff in the book. Any other questions?
How does TensorFlow handle overfitting or structure learning when you're creating different models?
What was the second thing you said? So overfitting or?
Structural learning, like say you were making a neural net, like how many nodes each particular layer should have?
I think TensorFlow I'm definitely not like an expert in the training, but I think it's the same as any machine learning framework. There's so many different algorithm things you can choose when you're doing the training, right? There are a lot of them out there. This is a Microsoft cheat sheet with all of them in, and in all cases, you have the underfit and overfit problem. So, I showed you guys the neural net earlier. If you put a really big hidden layer, to take a stupid example, like I have 100 training images and I have 100 nodes in my hidden layer, well, it's just going to remember the 100 images you trained it on. So there's this balancing act where you need to fit the size of the model to the size of the data you're training it with. Which is really subtle when you think about it. Like some of them are obvious. This is like the points. This is which model do I choose here to pick the right line. A linear model on the left is obviously too simple. Doesn't match. On the right, you've overfitted because you've got like this crazy complex thing that's just learnt the data. So I don't think it's, I'm definitely not an expert, but TensorFlow's job is probably not to solve the underfit and overfit problem. There are ways, the accuracy testing is supposed to solve some of that, because if your accuracy is not improving as you're training, it's sort of saying to you, oh, I might pick something wrong in my configuration here. I'm I'm not too familiar with the structural learning part of the question, but I think it's really hard to train these things. I don't think we're at the point yet that it's going to figure it all out for you. Yeah, I think I'd probably have to pass on the detailed answer to that. But you definitely still have the overfit and underfit problem. And it's getting into, you need to be a bit of a machine learning expert to figure that out.